This chapter discusses Structured Query Language, or SQL. It is based upon our book, Principles of Database Management, published by Cambridge University Press. You can find more information about our book on the website at the bottom of my slide. My name is Bart Baasens, and I'm one of the authors of the book. SQL is the lingua franca of RDBMSs and one of the most popular data definition and manipulation languages in use in the industry nowadays. Its core functionality is implemented, with only some minor variations, throughout all RDBMS products. This chapter discusses the SQL language constructs to express a relational model and to formulate queries that retrieve and modify the data in a relational database. First, we provide an overview of the SQL Data Definition Language, SQL DDL, to define a relational data model. We also discuss how the SQL Data Manipulation Language, SQL DML, can be used for data manipulation such as retrieving data, updating data, inserting new data, and deleting existing data. We then elaborate on SQL views and SQL indexes, which are part of the external and internal data model respectively. We also illustrate how SQL can be used for authorization by granting or revoking privileges to users or user accounts. The chapter concludes by illustrating how SQL can be used for managing metadata. Relational databases are based upon the relational data model and managed by a relational database management system, or RDBMS. Structured Query Language, or SQL, is the language which is used for both data definition and data manipulation. It is one of the most popular database languages currently in use in the industry. In what follows, we elaborate on its key characteristics and position it in terms of the three-layer database architecture. Note that SQL is sometimes also pronounced as SQL. Various versions of the SQL standard have been introduced, starting with the first, SQL 86, in 1986, and the most recent one in 2011, SQL 2011. It was accepted as a standard for relational data definition and manipulation by the American National Standards Institute, ANSI, in 1986 and by the International Organization for Standardization, ISO, in 1987. Note that each relational database vendor provides its own implementation, also called SQL dialect, of SQL, in which the bulk of the standard is typically implemented and complemented with some vendor-specific add-ons. SQL is primarily set-oriented and declarative. In other words, as opposed to record-oriented database languages, SQL can retrieve and manipulate many records at a time. Hence, it operates on sets of records instead of individual records. Furthermore, you only need to specify which data to retrieve, in contrast to procedural database languages, which also require to explicitly define the navigational access path to the data. In most RDBMS environments, SQL is implemented as a free-form language. In other words, no special indentation is required, as is the case for languages such as Python or COBOL. Most SQL implementations are case insensitive. It is, however, recommended to adopt a consistent formatting style to facilitate the understanding and maintenance of your SQL queries. SQL can be used both interactively from a command prompt or executed by a program written in a particular programming language, for example Java, Python, and many others. In that case, the general purpose programming language is called the host language, to the SQL code. Here you can see an example of using SQL interactively in a MySQL environment. MySQL is an open source RDBMS which can be freely downloaded from the web. It is very popular in the industry. In this screenshot, you can see that a query has been entered in the query window at the top. We explain later how this query works, but it basically selects all product numbers and product names of products for which more than one order line is outstanding. The query can then be executed and the result displayed in the result window below. Other RDBMSs such as Microsoft SQL Server, Oracle, and IBM DB2 also provide facilities to execute queries in an interactive way whereby a user can enter SQL queries, run them, and evaluate the results. Here you can see the same query but now executed by a host language, Java in this case. You can see the Java program at the top and the corresponding results in the console window below. DBMSs typically expose many application programming interfaces or APIs, through which client applications, written in Java for example, that wish to utilize the services provided by a DBMS can access and query a DBMS. This figure illustrates the positioning of SQL across the three-layer database architecture. At the internal data model layer, we find the SQL database, SQL tablespace, and SQL index definitions. At the logical data model layer, we have the SQL table definitions, whereby a table corresponds to a relation from the relational model. At the external data model layer, SQL views are defined, which essentially offer a tailored set of data for one or more applications or queries. The queries can be implemented in a host language or in an interactive environment. Remember, these layers should be connected but loosely coupled, such that a change in one layer has minimal to no impact on all other layers above. The SQL DDL and DML statements are clearly separated to successfully implement the three-layer database architecture. The Data Definition Language, or DDL, is used by the database administrator, DBA, to express the database's logical internal and external data models. These definitions are stored in a catalog. In what follows, we discuss the key DDL concepts and illustrate them with an example. We revisit referential integrity constraints and elaborate on how to drop or alter database objects. A key concept to start off with is the SQL scheme. This is a grouping of tables and other database objects such as views, constraints, and indexes which logically belong together. An SQL scheme is defined by a scheme name and includes an authorization identifier to indicate the user or user account who owns the scheme. Such users can perform any action they want within the context of the scheme. A scheme is typically defined for a business process or context, such as a purchase order or HR system. Here you can see the SQL definition of a scheme called purchase, whereby B. Bosons is assigned as the owner. Once we have defined a scheme, we can start creating SQL tables. An SQL table implements a relation from the relational model. It typically has multiple columns, one per attribute type, and multiple rows, one for each tuple. An SQL table can be created using the create table statement followed by the name of the table. You can see two examples of this. The first one creates a table product which is assigned to the default scheme. The second example creates a table product within the purchase scheme. It is recommended to explicitly assign a new table to an already existing scheme to avoid any confusion or inconsistencies. An SQL table has various columns, one per attribute type. As an example, our SQL table product can have columns such as product number, product name, product type, etc. Each of these columns has a corresponding data type to represent the format and range of possible values. This table gives some examples of commonly used SQL data types. Note, however, that these data types might be implemented differently in various RDBMSs, and it is recommended to check the user manual for the options available. In SQL, it is also possible for a user to define a data type or domain. This can be handy when a domain can be reused multiple times in a table or scheme. Changes to the domain definition then only need to be done once, which greatly improves the maintainability of your database scheme. Here you can see an example of domain, prod type domain, which is defined as a variable number of characters of which the value is either white, red, rosé, or sparkling. If you would decide later to also include beer, then this can be easily added to the list of admissible values. Note, however, that some RDBMSs, such as MySQL, do not support the concept of an SQL domain. SQL column definitions can be further refined by imposing column constraints. The primary key constraint defines the primary key of the table. Remember, the primary key should have unique values, and null values are thus not tolerated. This is the entity integrity constraint. A foreign key constraint defines a foreign key of a table, which typically refers to a primary key of another or the same table, hereby restricting the range of possible values. This is a referential integrity constraint. A unique constraint defines an alternative key of a table. A not null constraint prohibits null values for a column. A default constraint can be used to set a default value for a column. Finally, a check constraint can be used to define a constraint on a column values. All these constraints should be set in close collaboration between the database designer and business user. Let's now illustrate the DDL concepts discussed before with an example. This figure shows an ER model for a purchase order administration, which we'll also use to illustrate both SQL DDL and SQL DML in this chapter. Let's spend some time understanding it. We have three entity types: supplier, purchase order, and product. A supplier has a unique supplier number, which is its key attribute type. It is also characterized by a supplier name, supplier address, supplier city, and supplier status. A purchase order has a unique purchase order number, which is its key attribute type. It also has a purchase order date. A product has a unique product number, which is its key attribute type. It also has a product name, product type, and available quantity. Let's now look at the relationship types. A supplier can supply minimum 0 and maximum n products. A product is supplied by minimum 0 and maximum m suppliers. The supplier's relationship type has two attribute types: purchase price and delivery period, representing the price and period for a particular supplier to supply a particular product. A supplier has minimum 0 and maximum n purchase orders on order. A purchase order is on order with minimum 1 and maximum 1, or in other words, with exactly one supplier. Purchase order is existence dependent on supplier. purchase order can have several purchase order lines, each for a particular product. This is the relationship type between purchase order and product. A purchase order can have minimum 1 and maximum n products as purchase order lines. Vice versa, a product can be included in minimum 0 and maximum n purchase orders. The relationship type is characterized by the quantity attribute type, representing the quantity of a particular product in a particular purchase order. Here you can see the corresponding relational tables for our ER model. Note that primary keys are underlined and foreign keys are in italics. The supplier and product table correspond to the supplier and product entity types. The supplies table is needed to implement the N-to-M relationship type between supplier and product. Its primary key is a combination of two foreign keys, supplier number and product number. It also includes both the purchase price and delivery period, which were the attribute types of the relationship type supplies. The purchase order table corresponds to the purchase order entity type in the ER model. It also has a foreign key, supplier number, which refers to the supplier number in the supplier table. The PO line table implements the N-to-M relationship type between purchase order and product. Its primary key is again a combination of two foreign keys, purchase order number and product number. The quantity attribute type is also included in this table. The DDL definition for the supplier table is shown at the top of my slide. The supplier number is defined as char4 and set to be the primary key. We could have also defined it using a numbered data type instead, but let's say the business asked us to define it as 4 characters, so to also accommodate some older legacy product numbers which may occasionally include alphanumeric symbols. Subname is defined as a not null column. The DDL definition for the product table is shown at the bottom of my slide. In the product table, the prod number column is defined as the primary key. The prod name column is defined as not null and unique. Hence, it can be used as an alternative key. The prod type column is defined as a variable number of characters up to 10. Its values should either be wine, red, rosé, or sparkling. The available quantity column is defined as integer. The DDL for the supplies table is shown here. The supplies table has 4 columns. First, the supplier number and product number are defined. The purchase price is defined as 8, 2. It consists of a total of 8 digits with 2 digits after the decimal point. The delivery period column is assigned the time data type. The primary key is then defined as a combination of supplier number and product number. The foreign key relationship is then also specified. Neither of the foreign keys can be null, since they both make up the primary key of the table. The onUpdate cascade and onDelete cascade statements are discussed in a moment. Next, we have the purchase order table. The purchase order table is defined with the purchase order number, purchase order date, and supplier number columns. The latter is again a foreign key. We conclude our database definition with the purchase order line table. It has 3 columns: purchase order number, product number, and quantity. Both purchase order number and product number are foreign keys and make up the primary key of the table. Remember, the referential integrity constraint states that a foreign key has the same domain as the primary key it refers to and either occurs as a value of the primary key or null. The question now arises what should happen to foreign keys in case a primary key is updated or even deleted. As an example, Suppose the supplier number of a supplier tuple is updated or the tuple is deleted in its entirety. What would have to happen to all other referring supplies and purchase ordered tuples? This can be specified by using various referential integrity actions. The onUpdate cascade option says that an update should be cascaded to all referring tuples. Similarly, the onDelete cascade option says that the removal should be cascaded to all referring tuples. If the option is set to restrict, the update or removal is halted if referring tuples exist. Set null implies that all foreign keys in the referring tuples are set to null. This obviously assumes that a null value is allowed. Finally, set default means that the foreign keys in the referring tuples should be set to their default value. This is illustrated here. We listed some tuples of the supplier table. Let's focus on supplier number 37, whose name is ad fundum. This supplier has 4 referring supplies tuples and 5 referring purchase order tuples. Suppose now that we update the supplier number to 40. In case of an onUpdate cascade constraint, this update will be cascaded to all 9 referring tuples, where the supplier number will thus also be updated to 40. In case of an onUpdate restrict constraint, the update will not be allowed because of the referring tuples. If we now remove supplier number 37, then an onDelete cascade option will also remove all 9 referring tuples. In case of an onDelete restrict constraint, the removal will not be allowed. The constraints can be set individually for each foreign key in close collaboration with the business user. The drop command can be used to drop or remove database objects such as schemes, tables, views, etc. It can also be combined with the cascade and restrict options. Some examples are shown here. The first statement drops the purchase scheme. The cascade option indicates that all referring objects such as tables, views, indexes, etc. will also be automatically dropped. If the option would have been restrict, such as in the second example, the removal of the scheme will be refused if there are still referring objects such as tables, views, indexes. The same reasoning applies when dropping tables, as you can see illustrated. The alter statement can be used to modify table column definitions. Common actions are adding or dropping a column, changing a column definition, or adding or dropping table constraints. Here you can see 2 examples. The first one adds the prod image column to the product table and defines it as a binary large object or blob. The second example assigns a default value of 10 to the substatus column. Once we have finalized the data definitions, we can compile them so that they can be stored in the catalog of the RDBMS. The next step is then to start populating the database. This figure shows some examples of tuples listed for the various tables we defined earlier. We continue with the relational database for a wine purchase administration whereby the products represent wines. The Data Manipulation Language, or DML, retrieves, inserts, deletes, and modifies data. From a DML perspective, SQL defines 4 statements. The select statement retrieves data from the relational database. The insert and delete statements add and remove data. Finally, the update statement modifies data. In what follows, we zoom into each of these separately. We start with a brief overview of the SQL select statement. We then discuss simple queries, queries with aggregate functions, queries with group by having, queries with order by, join queries, nested queries, correlated queries, queries with all or any, queries with exists, queries with subqueries in select from, and queries with set operations. You can see the full syntax of an SQL select statement illustrated here. By using the options listed, we can ask very specific and complex questions to the database. In what follows, we elaborate on all these options. It is important to note that the result of an SQL select statement is a multiset and not a set. Remember, in a set, there are no duplicates and the elements are not ordered. In a multiset, sometimes also called bag, the elements are also not ordered. However, there can be duplicate elements in a multiset. As an example, you can think of a set with elements 10, 5, and 20, and a multiset with elements 10, 5, 10, 20, 5, and 10, where the elements 5 and 10 each occur multiple times. SQL will not automatically eliminate duplicates in the result. There are various reasons for this. First, duplicate elimination is an expensive operation. Next, the user may also want to see duplicate tuples in the query result. Finally, duplicates may also be considered by aggregate functions, as we illustrate later. Simple queries are SQL statements that retrieve data from only one table. In other words, the from component in the select statement contains only one table name. The select component then extracts the columns required. It can contain various expressions, which generally refer to the names of the columns we are interested in. Query 1 selects all information from the supplier table. In other words, it provides a complete table dump. In case all columns of a table are requested, SQL provides a handy shortcut notation, which is select asterisk from supplier. Here you can see the result displayed. It is also possible to select only a few columns as illustrated by query 2. As shown in the figure, this query selects the supplier number and supplier name from the supplier table. Query 3 selects the supplier number from the purchase order table. Since a supplier can have multiple purchase orders outstanding, the same supplier number can appear multiple times in the result, as you can see illustrated. Remember, the result of an SQL query is a multiset. That's why we see supplier numbers 32 and 37 appearing multiple times. Query 4 adds the distinct option. This option removes duplicates and makes sure that only distinct values are shown in the result, as illustrated. Query 5 shows that we can also include simple arithmetic expressions in the select statement. It selects the supplier number, product number, and delivery period divided by 30 from the supplies table. Remember, the delivery period was expressed in days, so if we divide it by 30, we can approximate it in terms of months. Note that we also added month deliv period as an alias or shortcut name to the calculation. The SQL queries we discussed thus far only included a select and from component. A missing where clause indicates there is no condition on the actual tuple selection. When a where clause is added to the SQL statement, it specifies selection conditions to indicate which table rows should be selected. Several operators can be used in the where clause, such as comparison operators, Boolean operators, the between operator, the in operator, the like operator, and the null operator. Let's illustrate this with some examples. Query 6 selects the supplier number and supplier name from the supplier table of all suppliers living in San Francisco. Query 7 selects the supplier number and supplier name from the supplier table of all suppliers living in San Francisco and whose status is higher than 80. Note that both conditions are combined with the Boolean AND operator. Query 8 selects the supplier number, name, and status from the supplier table of all suppliers whose status is between 70 and 80. Query 9 selects the product number and product name of all products whose product type is either white or sparkling. Note the use of the in operator, which combines the strings white and sparkling into a set. Query 10 illustrates the use of the percentage sign as a wildcard representing 0 or more characters. Another popular wildcard is the underscore, which is a substitute for a single character. In our example, we select the product number and product name of all products having the string heart as part of their product names. This selects all the Chardonnay wines as you can see illustrated. The keyword null can also be handy when formulating queries. For example, Query 11 selects the supplier number and supplier name of all suppliers whose status is null. Several expressions can be added to the select statement to ask for more specific information. These may also include aggregate functions used to summarize information from database tuples. Popular examples are count, sum, average, variance, min-max, and standard deviation. Let's work out some examples using the tuples illustrated here. Query 12 selects the number of tuples in the supplies table where the product number equals 178. For our example, the result of this query will be the number 5. Note the use of the count operator. Query 13 selects the number of not null purchase price values in the supplies table for tuples where the product number equals 178. The result will be the number 4, referring to the values 16.99, 17.99, 16.99, and 18. Note that the value 16.99 is counted twice here. If we want to filter out duplicates, then we can add the keyword distinct to the query as shown in query 14, which will obviously result in the value 3. Query 15 selects the product number and sum of the quantities, as calculated by sum quantity, of all PO line tuples of which the product number equals 178. The result of this query is 178 and the value 9, which equals 3 plus 6, as you can see illustrated. Query 16 simply adds up all the quantities of the PO line table, which results in the value 173. Query 17 selects the product number and average purchase price from the supplies table for all tuples where the product number equals 178. The result of this query is a weighted average price, since duplicate values will not be filtered out in the calculation. More specifically, since supplier number 37 and 69 both adopt a price of 16.99, this price will be counted twice, resulting into a weighted average price of 16.99 plus 17.99 plus 16.99 plus 18 divided by 4, or 17.4925. Hence, the result of this query will be the values 178 and 17.4925. In case we are interested in an unweighted average, then we need to add the distinct option, as you can see in query 18. Here, the value 16.99 will only be counted once, resulting into an average of 16.99 plus 17.99 plus 18 divided by 3, or 17.66. The variance, which represents the average squared deviation from the average, can also be calculated using variance purchase price, as shown in query 19. Query 20 selects the product number, minimum price, calculated using min purchase price, and maximum price, calculated using max purchase price, of all supply tuples for which the product number equals 178. This results into the values 16.99 and 18, as you can see. Let's add some more complexity to our queries by using a group by having clause. The idea here is to apply aggregate functions to subgroups of tuples in a table, where each subgroup consists of tuples that have the same value for one or more columns. By using the group by clause, rows are grouped when they have the same value for one or more columns, and the aggregation is applied to each group separately, instead of to the table as a whole, as in the previous examples. The having clause can then be added to retrieve the values of only those groups that satisfy specified conditions. It can only be used in combination with a group by clause and can include aggregate functions such as sum, min, max, and average. Let's start with query 21 as an illustration. This query retrieves the product numbers with at least 3 outstanding orders. If you look at the PO line table at the right, you see that both product number 212 and product number 900 satisfy the condition. The group by product number clause makes groups based upon the product number. You can see those groups represented here. We have a group for product number 212, for product number 178, and so on. The having count star bigger than or equal to 3 clause counts how many tuples are in each group and sees whether this is more than or equal to 3, in which case the product number will be reported. For the group with product number 212, the count star gives 3. And since this is more than or equal to 3, the product number 212 will be reported. For the group with product number 178, the count star results in 2, such that no output will be generated. Therefore, the resulting output will be product number 212 and 900 as shown. Query 22 assumes we want to retrieve the product numbers of products where the total order quantity exceeds 15. This can again be done using a group by having clause as shown. First, groups are made based upon the product number. The having sum quantity bigger than 15 clause then calculates the sum of the quantities within each group, and if this is bigger than 15, the product number and quantity will be reported in the output. Note that you cannot include this kind of selection criterion simply in the where clause, since the where clause expresses selection conditions on individual tuples in the table. Instead, the having clause defines selection conditions on groups of tuples based on a specified aggregate value calculated over each group. As you can see in the figure, the product number 212 group has 3 entries, for which the total outstanding quantity is 23, and the product number 668 has 2 entries, for which the total outstanding quantity is 16. Using the order by statement, SQL allows the user to order the tuples in the result of a query by the values of one or more columns. Each column, specified in the select clause, can be used for ordering, and you can sort by more than one column. The default sorting mode is ascending. Depending upon the commercial implementation, null values may appear first or last in the sorting. Query 23 retrieves a list of outstanding purchase orders, ordered ascending by date and descending by supplier number. Query 24 selects the product number, supplier number, and purchase price of all supplies tuples where the product number is 178. The result is sorted by purchase price in a descending mode. The number 3 in the order by statement refers to the third column, which is purchase price. Note that in this implementation, the null values appear last. Until now, we only discussed simple SQL queries, where data was retrieved from a single table. Join queries allow the user to combine or join data from multiple tables. In what follows, we discuss both inner and outer joins. Let's assume that we start from the supplier table, which contains supplier number, name, address, city, and status, and a supplies table, which contains supplier number, product number, purchase price, and delivery period. You now want to retrieve the supplier number, name, and status from the supplier table along with the product numbers they can supply and corresponding price. To do this, we first list the tables from which we need information, as shown here. At the bottom, you see some example tuples from both tables. Note that each table also contains additional information we do not need. We have 2 tables with corresponding information that we need to combine or join in a specific way. The question is, how? First, note that there are columns in each table with the same name, more specifically, sub number. Instead of using the verbose supplier.subnumber and supplies.subnumber notation, we use a shorthand notation. In this case, we will add R referring to the supplier table and S referring to the supplies table. This gives us R.subnumber and S.subnumber to differentiate both supplier numbers. Therefore, our first attempt to solve the question is query 25. What is this query doing? Since we have no word component, it will make the Cartesian product of both tables by combining every possible tuple from the supplier table with every possible tuple from the supplies table. This results in incorrect matchings as illustrated here. For example, you can see that supplier number 32, which is Best Wines, from the supplier table is now combined with supplier number 21 from the supplies table and many other incorrect matchings. This is clearly not what we want. To solve this, we need to carefully define under which conditions the join can take place by adding a where clause to our SQL join query. With an additional where clause, our SQL join query reads as shown here. In this query, the tuples can be joined only if the supplier numbers are identical. This is why it's called an inner join. You can see that the matchings are correct in the resulting tuples shown here. The data of supplier number 21 from the supplier table is correctly joined with data of supplier number 21 from the supplies table, and likewise for the other suppliers. Here you can see another equivalent way of expressing an SQL join query using the inner join keyword. Both queries 26 and 27 give identical results. It is also possible to join data from more than two tables. Assume we are interested in the following. For each supplier with outstanding purchase orders, retrieve supplier number and name, together with the purchase order numbers, their date, and the product numbers, names, and quantities specified in these purchase orders. We can again start by listing all the tables needed. We now need data from four tables: supplier, product, purchase order, and purchase order line. We need to use the primary foreign key relationships to specify our join conditions to ensure that correct matches are made. Our SQL join query is shown here. Again, note the shorthand notation that we use to refer to the tables. The where clause specifies all the join conditions. It should be noted that since data from four tables needs to be joined, this query is very resource intensive. The result is displayed here. In SQL, it is possible to join rows that refer to the same table twice. In this case, we need to declare alternative table names called aliases. The join condition is then meant to join the table with itself by matching the tuples that satisfy the join condition. Suppose we want to retrieve all pairs of suppliers who are located in the same city. It is obvious that we need data from only one table, supplier. However, we need to join this table with itself to solve the question. More specifically, the SQL query is shown here. Note that we introduce two aliases, R1 and R2, to refer to the supplier table. The join condition is now based upon matching subcity. However, there's another condition added, R1.subnumber less than R2.subnumber. What would be the rationale for this? The top figure shows a dump of the supplier table, which is the same for both R1 and R2. If we omit the condition R1.subnumber less than R2.subnumber, then the query result will also include duplicates such as deli wines, best wines, app funum, best wines, the wine depot, best wines, etc. because these have matching values for subcity. To filter out these meaningless duplicates, we added the condition R1.subnumber less than R2.subnumber. Only one result remains then, best wines, whose subnumber is 32, and the wine depot, whose subnumber is 68, which are both located in San Francisco. Essentially, any condition can be added to the join condition. Suppose we want to select the names of all suppliers who can supply product number 899. We need data from two tables, supplier and supplies, which should again be joined. The SQL query then becomes as shown here. The result of it is the wine crate. Remember, the result of an SQL query is a multiset, which may contain duplicates. If we want to eliminate duplicates from the result, we can use the keyword distinct. Assume the following request. Retrieve the names of all the suppliers who can supply at least one type of rosé wine. To answer this question, we need data from three tables: supplier, supplies, and product. In some cases, a supplier can supply more than one type of rosé wine and may appear multiple times in the result. This can be avoided by using the distinct option, as in query 31. You can see the result of the same query both without, see the left figure, and with, see the right figure, distinct option. Since Deli Wine supplies multiple rosé wines, it appears multiple times if the distinct option is not used. A join condition can also be combined with any of the earlier SQL constructs we discussed. This allows for the building of very powerful SQL queries, answering complex business questions. Let's consider the following example. Find the product number, name, and total ordered quantity for each product that is specified in a purchase order. We need data from two tables, product and PO line. The SQL query becomes as shown here. This query first joins both tables based upon corresponding product number. The group by clause then groups the join result by corresponding product number. For each group, the product number, product name, and sum of the order line quantity are reported. You can see the result at the bottom. The joins we have covered thus far are all examples of inner joins. This means that we always require an exact match before a tuple can be reported in the output. An outer join can be used when we want to keep all the tuples of one or both tables in the result of the join, regardless of whether or not they have matching tuples in the other table. In a left outer join, each row from the left table is kept in the result. If no match is found in the other table, it will return null values for these columns. Consider the following example. Retrieve number, name, and status of all suppliers, and if applicable, include number and price of the products they can supply. In other words, we want information of all the suppliers, even if they cannot supply any products at all. This can be solved using an outer join between the supplier and supplies table as shown by query 33. The left outer join clause indicates that all tuples from the supplier table should be included in the result, even if no matches can be found in the supplies table. The bottom figures illustrate some example tuples from both the supplier and supplies table. The result of the outer join query is displayed here. Note the tuple in boldface. This is supplier number 52, Spirits & Co. This supplier has no corresponding supplies tuples. It could be a new supplier for which no supplies have yet been entered in the database. Because of the left outer join clause, this supplier is now appearing in the end result with null values for the missing columns of the supplies table. In the right outer join, each row from the right table is kept in the result, completed with null values if necessary. Assume we have the following request. Select all product numbers, together with the product name and total ordered quantity, even if there are currently no outstanding orders for a product. This can be answered using a right outer join between the tables product and PO line. More specifically, the SQL query becomes as shown here. The PO line and product table are joined using a right outer join based on product number. This means that all products will be included, even if they are not included in any purchase order line. Next, the group by clause will make groups in this join table. For each group, the product number, product name, and sum of the quantity will be reported. You can see the result of this at the bottom. Note that for product number 119, which is Chateau Miraval, the quantity is null. Also for product numbers 154, 199, and 289, the quantity is null. These are now included in the end result because of the outer join. SQL queries can also be nested. In other words, complete select from blocks can appear in the work clause because complete select from blocks can appear in the work clause of another query as illustrated here. The subquery, or inner block, is nested in the outer block. Multiple levels of nesting are allowed. Typically, the query optimizer starts by executing the query in the lowest level inner block. Subqueries try to solve queries in a step-by-step sequential way. Assume we want to find the name of the supplier where a purchase order with number 1560 is placed. We need data from two tables, supplier and purchase order. We can now formulate a nested SQL query as shown here. To solve this query, the query optimizer first solves the inner block, which is select subnumber from purchase order where purchase order number equals 1560. The result of this inner block is 32, which is a scalar. That's why this is sometimes also referred to as a scalar subquery. We can now solve the outer block query, which becomes select subname from supplier where subnumber equals 32. The result of this query is best wines. Note that this query can also be solved using an inner join as discussed before. Consider the following example. Retrieve product number and name for each product that exceeds the available quantity of product 178. We only need one table to solve this question, product. The nested SQL query becomes as shown here. Again, the inner block is solved first. This is again a scalar subquery resulting into the scalar 136. The outer block can then be solved next. The result is shown at the bottom. The work component of an outer select block can contain an in operator followed by a new inner select block. Let's say you want to retrieve all supplier names who can supply product 178. To solve this, we need data from the supplier and supplies table. The nested SQL query becomes as shown here. Again, the inner block is solved first, which is select subnumber from supplies where product number equals 178. The result of this inner block is no longer a scalar, but a multiset of values, being in our case 21, 37, 68, 69, and 94. The outer block can then be evaluated, which now becomes select subname from supplier where subnumber in 21, 37, 68, 69, 94. This query then results in the supplier names depicted to the right. As already mentioned, multiple levels of nesting are allowed. Assume we want to retrieve all supplier names who can supply at least one type of rosé wine. This can be solved using a query with two subqueries as illustrated here. To execute this query, the RDBMS starts at the lowest level of nesting and works its way up. Note that this query can also be solved using an inner join across the tables supplier, supplies, and product. Here is another example of a nested query. We are interested in finding the product names that supplier 32 as well as supplier number 84 can supply. To solve this query, we need information from both the product and supplies table. The nested SQL query becomes as shown here. We now have two subqueries at the same level. If the computing architecture supports it, both subqueries can be executed in parallel, which allows to speed up query execution. In all previous cases, the nested subquery in the inner select block could be entirely solved before processing the outer select block. This is no longer the case for correlated nested queries. Whenever a condition in the work class of a nested query references some column of a table declared in the outer query, the two queries are said to be correlated. The nested query is then evaluated once for each tuple or combination of tuples in the outer query. Let's give some examples. Assume we want to retrieve the product numbers of all products with at least two orders. This is a very simple request at first sight. We need data from two tables, product and PO line. The question can be solved using the correlated SQL query at the top of my slide. As previously, the RDBMS starts by evaluating the inner select block first, which reads select count star from PO line pol where p.product number equals pol.product number. This is an example of a correlated query because the inner block refers to table P, which is declared in the outer block. Hence, this subquery cannot be processed because the variable P and thus p.product number are not known here. To solve this correlated query, the RDBMS iterates through each product tuple of the product table declared in the outer block and evaluates the subquery for the given tuple each time. Let's give an example. The left figure shows some example tuples from the product table. Remember, the tuples in a table are not ordered. The first product has product number 212. The subquery is now evaluated with this product number. In other words, it becomes select count star from PO line pol where 212 equals pol.product number. The result of this subquery is 3, as you can see in the PO line table to the right. Since 3 is bigger than 1, the product number 212 will be reported in the output. This process is then repeated for all other product numbers, resulting in the product numbers 212, 977, 900, 306, 783, 668, 766, and 178 as output of query 39. Basically, a correlated SQL query implements a looping mechanism, looping through the subquery for each tuple of the table defined in the outer query block. Correlated queries can answer very complex requests, such as the following. Retrieve number and name of all the suppliers who can supply a product at a price lower than the average price of that product, together with the number and name of the product, the purchase price, and the delivery period. The query needs information from three tables: supplier, supplies, and product. The first part of query 40 starts by specifying the join condition using the primary foreign key relationships. The second part then ensures that the price of the product is lower than the average price charged by all suppliers for the same product using a correlated subquery referring to the product table P defined in the outer select block. It is thus evaluated for every product tuple separately. This figure shows a visual representation of the query's functioning. Note that we use two appearances of the supplies table, S1 in the outer block and S2 in the correlated inner block. You can see that product number 178 can be supplied by supplier number 37 at a price of 16.99, which is clearly lower than the average of all prices charged by suppliers for product number 178. Let's now assume that we are interested in finding the three highest product numbers. This can be easily accomplished using an order by clause, but that will list all product numbers, which may not be very useful if you have many products. A correlated query can provide a better solution, as shown by query 41. Essentially, this query counts for each product the number of products with a higher product number. If this number is strictly smaller than 3, the product number belongs to the three highest product numbers and will be reported. Put differently, there is no product with a product number higher than the highest product number. There is only one product number which is higher than the second highest product number, and two product numbers which are higher than the third highest product number. The results of this correlated query are the product numbers 915, 977, and 900. The bottom figure illustrates the functioning of query 41. The inner query block is evaluated for each product number separately. For product number 119, which happens to be the smallest product number, the inner query becomes select count star from product P2, where 119 is less than P dot product number. The result of this query is 41, which is clearly not smaller than 3, so no output is given. For product numbers 900, 915, and 977, the inner block will yield 2, 1, and 0 respectively, which are all less than 3. Therefore, these product numbers will be output. Besides the in operator, which we already discussed, the any and all operators can also be used to compare a single value to a multiset. The comparison condition, v bigger than all v, returns true if the value v is greater than all the values in the multiset v. If the nested query doesn't return a value, it evaluates the condition as true. The comparison condition, v bigger than any v, returns true if the value v is greater than at least one value in the multiset v. If the nested query doesn't return a value, it evaluates the whole condition as false. Consider the following example. Retrieve the names of the suppliers who charge the highest price for the product with product number 668. This query needs information from both the supplier and supplies table. It can be solved using a nested query with the all operator as shown by query 42. The query has two levels of nesting. First, we start with the deepest level of nesting. The result of this subquery are the prices 6 and 6.99. The result of the next subquery is 68. The result of the outer block will then be the wine depot. This figure visualizes the functioning of query 42. You can see that the wine depot, which is supplier number 68, can supply product number 668 at a price of 6.99, which is higher than or equal to all other prices, in this case 6.99 and 6. Assume we are interested in the following information. Retrieve number, name, city, and status for each supplier who has the highest status of all the suppliers located in the same city. The SQL query becomes as shown here. This is an example of the ALL operator in combination with the correlated query. It is quite self-explanatory since it selects the supplier number, name, city, and status of a supplier R1 where the status is higher than or equal to the status of all suppliers R2 which are located in the same city as supplier R1. The result is displayed at the bottom. Let's now also illustrate the any operator. Suppose we want to retrieve the names of the suppliers who do not charge the lowest price for product number 178. This can be solved with query 44. This is a double-nested query, and we can start again with the lowest level subquery. The answer to this subquery is the multiset with elements null, 16.99, 17.99, 16.99, and 18. The next subquery can then be solved. The any operator returns true if the purchase price is greater than at least one value in the multiset. The result of this subquery then becomes 68 and 94. The outer select block can now be run, which gives the supplier names the wine depot and the wine crate. The exists function is another handy feature in SQL. It allows to check whether the result of a correlated nested query is empty or not. The result is a Boolean value, true or false. In general, exists returns true if there is at least one tuple in the result of the nested query, or otherwise returns false. Vice versa, the notExist function returns true if there are no tuples in the result of the nested query, or otherwise returns false. Because the exists function only evaluates whether or not a nested query outputs any rows, it is unimportant what is specified in the select component. Hence, one commonly uses select star for the subquery. Consider the following example. Retrieve the names of the suppliers who can supply product number 178. This can be easily solved by using either a join or nested subquery as we discussed before. Here, we present a third alternative using the exists function as shown by query 44. You can clearly see that the subquery is correlated, as it refers to the supplier table R defined in the outer select block. For each supplier, the correlated subquery is evaluated. As soon as it returns a result, the exists function will evaluate to true and the supplier name will be reported. You can see the result of this query displayed to the right. The exists function allows for complex requests such as the following: retrieve name, address, and city for each supplier who can supply all products. This question can be solved using a double correlated query with two notExist functions as shown by query 45. Basically, this query looks for all suppliers for whom there exist no products they cannot supply. Remember, the notExist function evaluates to true if the subquery does not return a result. This query starts from a specific supplier and then looks for all products that the supplier cannot supply. If there are no products the supplier cannot supply, then it means that he can supply all products and the supplier name will be reported. In our example, this query returns 0 rows, as there are no suppliers who can supply all products. Besides the where component, subqueries can also appear in the select or from component. Assume that we want to retrieve the product number, name, and total ordered quantity of each product, even if a product has no outstanding orders. We have solved this earlier using an outer join. An alternative is query 46. In this query, we have a subquery in the select component. This subquery results into a scalar representing the total ordered quantity for a specific product. As with the outer join, if no match can be found in the PO line table, a null value will be generated for the sum quantity expression. This is the case for product number 523, as you can see in the figure. Subqueries can also appear in the from component. Consider the following example. Retrieve all numbers of products where the difference between the maximum and minimum price is strictly bigger than 1. This can be solved by query 47. You can see that the from component has a table subquery which calculates the minimum and maximum price for each product. It uses a group by clause to accomplish this. Your subquery assigns the aliases min price and max price to the corresponding columns and the alias m to the overall result. These can then be used in the outer query, as you can see illustrated. The result of this query is shown below. Standard SQL also supports set operations such as union, intersect, and except to combine the results of multiple select blocks. Let's first refresh how these set operations work. Consider the following two sets A and B. The result of A union B is the set of all values that are either in A or in B. The result of A intersect B is the set of all values that are in A and B. The result of A except B is the set of all values that are in A but not in B. Hence, when applied to an SQL query, the result of the union operation is a table that includes all tuples that are in one of the select blocks or both. The result of the intersect operation is a table that includes all tuples that are in both select blocks. The result of the except operation is a table that includes all tuples that are in the first select block but not in the second. Duplicate tuples are by default eliminated from the result unless the all operator is added. Consider the following example. Retrieve number and name of suppliers who are located in New York or who can supply product number 915. This can be solved by query 48. Observe how the results of both queries are combined using the union operator. To successfully accomplish this, both select blocks should be union compatible in the sense that they ask for the same columns, in our case, subnumber subname and r.subnumber r.subname. The result is also sorted by supplier name by adding an order by clause to the end of the last select block. The result is shown at the bottom. Assume that we change the query as follows. Retrieve number and name of suppliers who are located in New York and who can supply product number 915. Both select blocks remain the same as you can see illustrated, but are now combined with the intersect instead of union operation. The result of this query is null. To conclude, consider the following request. Retrieve the number of the suppliers who cannot currently supply any product. This can be solved using two select blocks combined with an except operation as shown here. This query selects all supplier numbers which appear in the supplier table but not in the supplies table. The result of Q50 is supplier number 52. The SQL insert statement adds data to a relational database. The first statement inserts a new tuple into the product table. The values are entered according to the order in which the columns have been defined using the create table statement. The next statement is equivalent, but also explicitly mentions the column names. This is recommended to avoid any confusion. It is also possible to specify only a few column names, as illustrated by the third statement. The values for the unspecified columns then become null, if null is allowed, or the default value, if a default value has been defined. The first statement here adds 3 tuples to the product table. It is important to respect all constraints defined, such as not null, referential integrity, etc., when adding new tuples to a table. Otherwise, the insert will be rejected by the DBMS and an error notification will be generated. An insert statement can also be combined with a subquery. The second example inserts the supplier numbers of all suppliers that cannot supply any products in a new table, inactive suppliers. Data can be removed using the SQL delete statement. The first example removes the product tuple with product number 1000 from the product table. The second statement removes all supplier tuples from the supplier table where the supplier status is null. The delete statement can include subqueries. The third example removes all product numbers from the supplies table of products that have the string shard as part of their product name. This will remove the Chardonnay wines in the supplies table. A delete statement can also contain correlated subqueries. This is illustrated in the first example, which removes suppliers from the supplier table that have no corresponding tuples in the supplies table. The second example is a self-referencing delete. It removes all supplies tuples where the purchase price is strictly bigger than 2 times the average purchase price for a specific product. Removing all tuples from the product table can be done as shown in the third example. As discussed before, the removal of tuples should be carefully considered, as this may impact other tables in the database. Modifications to data can be made using the SQL update statement. The first example sets the available quantity to 26 for the product number 185 in the product table. The next update statement sets the supplier status to the default value for all suppliers. Update statements can include subqueries. The third example adds 7 days to the delivery period for all supplies of the supplier Deli Wines. An update statement can also contain correlated subqueries. The first update statement guarantees that supplier number 68 can supply all his products at the minimum price and delivery period. An update statement can be combined with an altered table statement. The altered table statement shown adds a column subcategory with default value silver to the supplier table. An update statement is then used to set the values of this new column. In case the supplier status is between 70 and 90, a gold status is assigned. In case it's higher than 90, it's set to platinum. Note the use of the case statement, which allows to implement if-then-else operations in SQL. The result is shown here. SQL views are part of the external data model. A view is defined by means of an SQL query, and its content is generated upon invocation of the view by an application or by another query. In this way, it can be considered as a virtual table without physical tuples. Views offer several advantages. By hiding complex queries, such as join queries or correlated queries, from their users, views facilitate ease of use. They can also provide data protection by hiding columns or tuples from unauthorized users. Views allow for logical data independence, which makes them a key component in the three-layer database architecture. Views can be defined using the create view statement. The first view is called top suppliers and offers the supplier number and supplier name of all suppliers whose status is bigger than 50. The second view refines the first by adding an additional constraint, subcity equals San Francisco. The order overview view contains the product number, product name, and total ordered quantity of all products. Note that the left outer join in the view definition ensures that products with no outstanding orders are also included in the result. Once the views have been defined, they can be used in applications or other queries as shown here. The first query selects all tuples from the view top suppliers as F, which we define above. The second query retrieves all tuples from the order overview view, where the product name contains the string short. The first option for DBMSs to perform queries on views is query modification, where the RDBMS modifies queries that query views into queries on the underlying base tables. View materialization is an alternative strategy in which a physical table is created when the view is first queried. To keep the materialized view table up to date, the DBMS must implement a synchronization strategy whenever the underlying base tables are updated. Synchronization can be performed as soon as the underlying base tables are updated, which is immediate view maintenance, or it can be postponed until just before data is retrieved from the view, also called deferred view maintenance. Some views can be updated. In this case, the view serves as a window through which updates are propagated to the underlying base tables. Updatable views require that insert, update, and delete statements on the view can be unambiguously mapped to inserts, updates, and deletes on the underlying base tables. If this property does not hold, the view is read-only. Let's reconsider our view order overview, which we defined earlier. The update statement tries to set the total ordered quantity to 10 for product number 154. Since there are multiple ways to accomplish this update, the RDBMS will generate an error. A view update is feasible when only one possible update on the base table or base tables can accomplish the desired update effect on the view. In other words, this is an example of a view which is not updatable. The with check option allows to check update and insert statements for conformity with the view definition. To illustrate this, consider these two examples of update statements on our top suppliers view, which has now been augmented with a with check option. The first update will be rejected by the RDBMS because the supplier status of supplier 32 is updated to 20, whereas the view requires the supplier status to be greater than 50. The second update statement will be accepted by the RDBMS because the new supplier status is bigger than 50. SQL also provides facilities to manage privileges. A privilege corresponds to the right to use certain SQL statements such as select, insert, etc. on one or more database objects. Privileges can be granted or revoked. Both the database administrator and scheme owner can grant or revoke privileges to or from users or user accounts. They can be set at account, table, view, or column level. The table provides an overview. Some examples of privilege statements in SQL are shown here. The first example grants select, insert, update, and delete privileges on the supplier table to user B-Bosons. The second grants a select privilege on the product number and product name columns of the product table to all public users. The third statement revokes the earlier granted delete privilege on the supplier table from user B-Bosons. The fourth statement grants select, insert, update, and delete privileges on the product table to user W-Lemailleux, whereby the with grant allows the user W-Lemailleux to grant the privileges to others. The fifth statement grants the user S. van den Broeke the privilege to define referential integrity constraints that refer to the supplier table. Note that this privilege allows inferring certain information from the supplier table, even if no privileges are granted to actually query the table. For example, a foreign key constraint in another table that refers to supplier number in the supplier table can be used to verify whether a certain supplier exists. It is important to stress that SQL privileges are often combined with views to exert fine-grained control over set of rows and columns in a table that can be accessed by a particular user. For example, the view definition and access privilege shown here can be used to express that user W-Lemailleux can only access the supplier number and supplier name columns in the supplies table and only for suppliers located in New York. Since most DBMSs in use are relational, the catalog itself can also be implemented as a relational database. Hence, this implies that SQL can be used to define and manage metadata. To illustrate this, let's first start from an EER conceptual model for a relational model as illustrated here. It includes the following entity types: table, column, key, primary key, and foreign key. Key is a superclass of the entity types primary key and foreign key. The specialization is total and disjoint. A table has a unique table name. Column is a weak entity type since its key is a combination of table name and column name. Hence, the same column name can be used in multiple tables. Relationship type R1 says that a table can have 0 to n columns, whereas a column always belongs to exactly one table. R2 indicates that a column can correspond to 0 or m keys, such as a primary and a foreign key, and a key to between 1 and n columns. R3 specifies the relationship between a table and its primary key. R4 models the relationship between a foreign key and the corresponding primary key. R5 indicates what table a foreign key belongs to. Using the mapping rules explained earlier, we can now map the ER model to the relational model shown here. Note that primary keys are underlined and foreign keys are put in italics. Once the catalog has been successfully implemented, it can be populated and queried using SQL, just as when working with raw data. The first SQL query retrieves all column information of the supplier table. The second SQL query retrieves the primary key of the supplier table, the names of the foreign keys referring to it, together with their tables and delete rules. To conclude, this clearly illustrates the power and beauty of SQL in an RDBMS environment. Using the same SQL DDL and SQL DML to manage both raw data and metadata contributes to the productivity and efficiency of database users when working with relational databases. In this chapter, we discussed SQL as one of the most important data definition and data manipulation languages for relational databases. We started by introducing the basic concepts of SQL and positioned it in terms of the three-layer database architecture. We then elaborated on the SQL DDL instructions which can be used to either create or remove database objects such as schemes, tables, domains. We extensively discussed SQL DML instructions by reviewing the select, insert, delete, and update statements. The next section covered SQL views, which are part of the external data model in a relational environment. We then elaborated on granting and revoking SQL privileges. The chapter concluded by reviewing how SQL can be used to manage relational metadata in a transparent way. This chapter is based upon our book, Principles of Database Management. If you want more information, I'm happy to refer to the website at the bottom of my slide.